Welcome back to Think Cosmos, where we ponder the universe's deepest secrets and wonders. Deep in the heart of our Milky Way galaxy lies a region we long thought of as a cosmic war zone, a place so tumultuous and intense that it was hard to imagine anything as delicate as a planet being born there. This is the Galactic Center, home to our galaxy's central, supermassive black hole, intense radiation, roaring stellar winds, and clouds smashing into each other. For years, astronomers assumed that this neighborhood was just too wild and hostile for the quiet, fragile process of planet formation. After all, how could tiny dust grains and pebbles gently come together to form planets, when everything around them is being stirred and heated like a cosmic hurricane? It would be like expecting a sandcastle to form in the middle of a tornado. But as it turns out, planets find a way. In a stunning discovery, scientists have detected signs of planetary nurseries right in the Milky Way's central molecular zone, essentially the rough downtown of our galaxy. Using the ultra-sharp vision of the ALMA telescope array in Chile, that's the Atacama Large Millimeter Submillimeter Array, an international team peered through the heavy shrouds of dust and gas toward the galactic center. What they found left them astonished. Hundreds of dense, compact disks and cores that appeared to be the early stages of star and planet formation, even under those extreme conditions. Let's put this in perspective. Most of the protoplanetary disks we've studied, those are the swirling disks of gas and dust around young stars, from which planets form, have been in relatively peaceful parts of the galaxy, like the star-forming regions near the sun or in the spiral arms farther up. These regions are comparatively calm. Sure, there are bright stars and supernovae occasionally, but nothing like the frenetic activity near the galaxy's core. Studying those suburban nurseries has given us a kind of biased comfort. Okay, planets can form around sun-like stars in nice, quiet regions. That makes sense. That's like our own solar system's history. The galactic center, though, is like downtown during rush hour multiplied by 1,000. High pressure, high density, shock waves from supernovae, intense magnetic fields, you name it. The ALMA survey targeted 3 specific clouds in the central molecular zone, often abbreviated CMZ. These are big, massive clouds of gas and dust sitting only a few tens of light years from the very center. They managed to create the most detailed map ever of these clouds at multiple radio wavelengths. And when they analyzed the data, they noticed little red dots scattered across the images. Those red dots weren't actual color, red invisible light, but a way of saying that at one frequency band, these objects were brighter relative to another band, suggesting a particular characteristic. They likely were self-absorbing at higher frequency, which is a signature of dense, dust-rich objects like protostellar disk. In simpler terms, those dots seem to be tiny, dense pockets where a baby star might be forming with a disk around it. How many did they find? Over 500 dense cores. And within those, potentially over 300 that could be protoplanetary disks. This was mind-blowing, because it means not just 1 or 2 flukes, but an entire population of would-be planetary systems forming right under the nose of the galactic center chaos. The researchers themselves were taken aback. They basically said, "We were astonished to see these little red dots cross the whole molecular cloud. It's nothing like what we expected." Initially, they might have thought they were just seeing clumps of gas, which is common. But the telltale spectral signature hinted these clumps had dust grains big enough to absorb millimeter waves strongly. Big dust grains are a clue. You need dust grains to start sticking together to eventually form pebbles, and planetesimals. And big grains usually form in the midplanes of disks around young stars, not just in random gas clumps with no star. So why is this so significant? It challenges our understanding of star and planet formation by extending it into a realm we thought was unfavorable. If planets can start forming here, they might form almost anywhere. It's like finding flowers blooming in the desert. It tells you life, or in this case, planet formation, is more tenacious than you assumed. The conditions in the CMZ, high temperatures, strong turbulence, lots of radiation, were thought to either blow apart disks or prevent them from cooling enough to form planets. Yet here we see evidence that maybe, just maybe, those processes adapt. Perhaps the disks in the galactic center are different. Maybe they're more massive or more tightly bound, allowing them to withstand the turbulence. Or perhaps planet formation can proceed faster under high pressure, so the seeds of planets take hold quickly in between disruptive events. One idea the team considered is that these red dot structures could be something else, like just dense cores without disks. But they found clues that point to disks. For example, certain spectral indices that suggest the presence of large dust grains. Large dust grains. Imagine sand or small pebbles, rather than fine smoke-like dust, are a fingerprint of disk environments. Because in free-floating cores, grains don't tend to grow that big before being disrupted, unless they are in a relatively sheltered, rotating disk around a new star. In fact, they weighed some possibilities. Maybe these are dense cores with embedded disks, or maybe even a weird scenario, like the cores have disks so big they almost mimic cores. Either way, it involves disks, in some quotes. A researcher noted the presence of these grains could only be explained if they formed in disks and then somehow got expelled. Perhaps by the outflows from infant stars, pushing dust outward into the cloud. That implies the disks are there, producing those grains. To give an example, one of the authors said, "It is exciting that we are detecting possible candidates for protoplanetary disks in the galactic center. The conditions there are very different from our neighborhood, and this gives us an opportunity to test our theories." That's a key point. Testing our theories. Our models of planet formation are based mostly on what we've observed locally. Now we have a natural laboratory to see if those models hold up or need tweaking for extreme environments. What could be different in these extreme environments? One thing is timescales. Maybe in the CMZ, things happen quicker. Higher density could mean faster collapse of clouds into stars, and perhaps disks might also evolve faster or be shorter-lived due to the environment. If disks have shorter lifespans near the galactic center, because maybe a nearby supernova blows them away, or the black hole's tidal forces shear them, then planet formation would have to be a more hurried process there. It's as if nature is speedrunning planet formation in the galactic downtown, whereas out in the galactic suburbs, it can take its leisurely time over tens of millions of years. Another difference: chemical makeup. The central regions have different chemistry, perhaps more heavy elements, because it's a hub where many generations of stars have lived and died. More heavy elements, metals in astrospeak, mean more solid material to build dust and planets. So ironically, even though it's violent, the galactic center might have lots of stuff to make planets, which could actually boost planet formation in some sense. It's like a double-edged sword, plenty of building material, but also lots of hazards. Now one might ask, what kind of planets could come out of such an environment? We don't know yet, but one might speculate that gas giants could be common, since high densities favor rapid core accretion before the gas is blown away. Or maybe only hardy rocky planets survive after the volatile stuff gets stripped. Or perhaps many planets form, but a lot of them end up on crazy orbits due to all the gravitational perturbations around, or get flung out of the system entirely. The truth is, this finding raises more questions than it answers, which is great for science, because it means a whole new avenue of research. For example, Now that we suspect these disks exist, the next step is to try to observe them more directly. Alma could try to zoom in on some of the brightest candidates and actually resolve disk-like structures, or look for molecules that typically trace disks, or other telescopes might look for signs of young stars, maybe by their infrared glow associated with those dots, confirming they are indeed forming stars. One thing to keep in mind: a disk detection isn't a planet detection. We haven't actually seen a planet there, just the likely cradles of planets. But statistically, if the environment supports disks, it almost certainly supports planets, because planet formation is a natural outcome of disk evolution. Given enough time and material, planets just happen as dust sticks, then pebbles, then rocks, etc. So it's reasonable to conclude that planets, maybe many planets, are forming in the Milky Way's core as we speak. This forces a delightful reconsideration of our assumptions about habitability and life too. We usually think the galactic habitable zone, if such a thing exists, is further out from the dangerous central regions, not too close to the big black hole, not too close to where supernovae pop off frequently, etc. And that's probably true for life as we know it. The center is bathed in radiation that would be problematic for life on a planet's surface. However, if planets do form there, could life ever find a way much later, in nooks and crannies or deep underground oceans perhaps, shielded from the radiation? Hard to say, but it's the basic requirement. Having planets appears to be met in principle. It's a bit like discovering an oasis in what you thought was a completely barren desert. It might not be a place you'd go sunbathing, but life could exist in sheltered pockets. Another implication of this discovery concerns how we simulate galaxies. Much like with the black hole winds, our galaxy formation models have to consider where planet formation happens, because that ties into how dust and heavy elements cycle through the galaxy. If the central zone forms planets, that means some fraction of dust is getting locked into those planets, at least temporarily, instead of being immediately available for other processes. It might not be a major factor on the grand scheme, but it's something to note. Also, the presence of disks could influence how we interpret observations of the galactic center. Some emissions could be coming from these disks or the young stars in them, for instance. Zooming out a bit, it's heartwarming in a way. Our galaxy's core is not too different from other parts of the galaxy after all, in the sense that starry nurseries are a universal phenomenon. It's like finding a small, quiet nursery tucked away in the heart of a bustling city. Life, or star life, goes on even amid chaos. It makes the Milky Way feel more unified as a system, with planet formation happening across its breadth. On a more philosophical note, this discovery highlights the theme that nature is resilient. Give it the slightest chance to form structure, and it will. We see this on Earth with life in extreme environments, like microbes in boiling acid springs. And here we see it with planet formation in extreme environments. It seems the universe has a penchant for creating complexity, even in harsh settings. The researchers dubbed their survey Duet, since they used dual bands, which is a nice name because it suggests a harmony of two different signals working together to reveal something. In a way, it took a duet of advanced technology and clever observing strategy to find this cosmic duet of stars and planets forming at the galactic center. So, what's next? Now that we suspect there are hundreds of potential baby planetary systems in those central clouds, astronomers will be chomping at the bit to follow up. Perhaps they will monitor these regions for outbursts. Young stars sometimes flare as they accrete material. It's called episodic accretion, and ALMA, or infrared telescopes, might catch variability. They might also try to detect certain molecules like HCN or QO in a way that indicates disk rotation. This discovery is a beginning of a story, not the end. we're going to learn a lot more about how these central zone disks differ from ones in, say, the Orion Nebula region, or around nearby young stars like those in the Taurus molecular cloud. Already one difference is apparent. The sheer number of them in a small volume implies star formation in the center, might produce many more low-mass stars with disks at once, possibly because the gas clouds there fragment into many pieces. It could be a very rich star-forming event. Let's not forget the human element. For decades, textbooks probably said, the galactic center is not conducive to planet formation. And now observers, perhaps some skeptics among them originally, have evidence that flips that narrative. It's a humbling reminder to never say never in astrophysics. Or the universe often finds a way to surprise us. As we marvel at the idea of planets forming in the Milky Way's most chaotic realms, one can't help but wonder, what would a sunrise look like from a planet orbiting a star near the galactic center? The sky might be awash with a dense star field, far richer than the one we see here. The neighborhood would be teeming with clusters and nebulae. Perhaps. Sure, there'd be hazards, radiation, etc., but also a grandeur to that sky that we can barely imagine. Any future space explorers, from Earth venturing towards the center, might find worlds beyond count, circling stars in that hectic region. For now, we can't see those planets directly. They're just infants, and our instruments aren't quite up to imaging them yet. But knowing they're likely, there is thrilling. It makes our galaxy feel more alive and complex. So the next time someone tells you an environment is too harsh for something beautiful to emerge, remember those little red dots at the center of the Milky Way. Even in the furnace and fury near a galaxy's heart, the seeds of new worlds are taking root. If planets can blossom in the galactic center, where else might we find life's potential footholds? It's a big, bustling universe out there, and it seems determined to fill every niche with wonders. Doesn't it spark your curiosity to think that even the most extreme corners of our galaxy could be brewing new worlds? What might those worlds be like? And could any of them, against all odds, harbor life in forms we've never seen?